Hi everyone, my name is Kevin. So today I'm going to be walking you through finding the electric field on the axis of a thin ring of charge. So essentially I split it into four different sections to kind of break it down. I call them sketch, conditions, substitutions, and calculations. So the sketch and the substitutions should be the easiest to come up with. It's the conditions that takes a little bit of memorizing and recognizing some geometric and trigonometric relationships. And the calculations is really the beast. There's a lot to deal with there. So first up, sketch. All right, so what we have here is basically we're trying to find the electric field on point P towards the right there. And we're going to use Z to represent the distance from P to the center of the ring along a perpendicular axis. R is going to be a distance from the center of the ring to basically Q, which is going to be the charge that's going to be having force upon P. Then Ri is going to be different. It's going to be the distance between Q and P right there. And so we're also going to need to find theta I there, and then as well as epsilon, we'll call it, and that's the angle from the x-axis to R. And also, don't get confused, the angle between R and Z in this is technically 90 degrees. It's just because we're looking at it in 3 dimensions here that it looks like it's greater than 90 degrees. And also, an underlying theme here, we need to recognize that we're really just going to need to find the force on the z-axis because it's along the perpendicular axis. All the vertical forces are going to cancel out from the ring, and you're just going to be left with the horizontal forces. All right, next up, let's talk about the conditions here. So some things you have to recognize. You have to recognize that the linear charge density, number one here, is equal to the charge over the length, Q over L. Rearrange that to get Q equals linear charge density times L. And then next you have to recognize that L, the length, is basically equal to the circumference of the ring, which would be 2 pi r. And finally, if you essentially take the derivative of that, you're going to get delta Q is equal to linear charge density times R times d epsilon, that second angle we had between the x-axis and R. And another thing we'll also have to recognize for a substitution later on is that the linear charge density is equal to Q over 2 pi r, and that's really just rearranging that third part of number 1 there. All right, I'm going to skip around a little bit. Number 3 here, need to recognize kind of one of the geometric relationships I was talking about here, that z squared plus r squared is going to equal ri squared. And then when you rearrange that, you're going to get Ri is equal to the radical of z squared plus r squared. All right, so then going up to number 2, using what we just did there, you need to recognize that the cosine of theta is equal to adjacent over hypotenuse, or in this case, it would be z over Ri, which Ri, the way we just found out, is radical z squared plus r squared. All right, next we're going to use those conditions that we just came up with to make some substitutions here. So once you come up with the conditions, these substitutions shouldn't be too bad. So first, kind of our main equation, we need to recognize that electric field EI in the z direction is going to equal the constant K, which is 1 over 4 pi epsilon naught, times delta Q over Ri squared times the cosine of theta, because we're really just interested in the forces along the z-axis there. All right, so using those substitutions, the K constant is going to stay the same. We're going to be changing delta Q to linear charge density times R times d epsilon, and then making a substitution for Ri below, which Ri squared is equal to z squared plus r squared. Then finally, we'll substitute for cosine theta, which is z over radical z squared plus r squared that we found out in our conditions. Alright, so now the most substantial part here, we'll start this out. So the calculations here, I rewrote that first equation there. That's what we just found out, and then we're pretty much going to be able to combine some terms there. So essentially in the second part of the term, you have z squared plus r squared. In the third part, you have radical z squared plus r squared. You can combine those to get z squared plus r squared to the power of 3 over 2. And then you also bring over the z and add it with those other constants in the numerator. All right, now that we have it simplified as much as we can, we're ready to take the integral. So pretty much you're able to drag out all of the constants outside the integral, and all that you're left with is the epsilon, and that's really the only thing you need to evaluate is that angle between the x-axis and r to really see how far around the ring it goes, which in this case, once you evaluate, it's going to be from 0 to 2 pi because it's essentially a whole circle. Alright, so that, again, that's it rewritten at the top right there. And so next thing, again, you can evaluate epsilon from 2 pi to 0, which really is just the angle. The actual integral of this is fairly simple. It's just going to be 2 pi minus 0. And then simplify, you can pretty much combine those terms, and then that 2 pi you're going to bring to the numerator, and that's going to the pi's are going to cancel out because we already have a 4 pi epsilon naught in the denominator. And then we're also going to have 2 over 4 for constants. So that would just be a 2 in the denominator. Alright, so now we need to make another substitution for one of the things that we found out in our conditions earlier on. So we basically need to recognize here that the linear charge density is equal to q over 2 pi r. So when we substitute that in, you get qrz at the top, and then that 2 pi r you're going to bring to the bottom right there. So you'll have the 2 that you already did times 2 pi r epsilon naught in the big Z and R term. And then finally, to get your final answer, you can simplify that. The r's will cancel out, and then you have the 2 times 2 at the bottom. So your final answer is the electric field at Z is equal to qz. The electric field along the z-axis, rather, is equal to qz over 4 pi epsilon naught times z squared plus r squared to the power of 3 over 2. So that's your final answer there. I hope this helped. The way I kind of set it up with the sketch conditions, substitutions, and calculations. All right, have a great day.